Hi everyone. Today's topic is expression for bandgap energy of intrinsic semiconductors in terms of electrical conductivity of the intrinsic semiconductor and resistance of the intrinsic semiconductor. We know that electrical conductivity of the metal usually expressed as N E square tau by M or N E into E tau by M. Here E tau by m is the mobility of the electrons in a metal. Therefore, sigma is equal to n mu and then E. N denotes the number of electrons per unit volume of the metal and E is the charge of the electron. The same formula we are going to use here, but here in an intrinsic semiconductor we have two types of charge carriers. One is the electron and another one is the hole. So here electrons and holes are the charge carriers. Therefore, electrical conductivity of an intrinsic semiconductor can be given by Ni E mu E plus mu H. The unit being ohm inverse, meter inverse. Here we are going to derive the expression for bandgap energy of the intrinsic semiconductor. The bandgap energy will be expressed usually as E with a subscript G, forbidden energy gap. Here Ni denotes the intrinsic carrier concentration, that is concentration of charge carriers in an intrinsic semiconductor per unit volume. The formula for intrinsic carrier concentration is 2 into 2 pi kBT by H square the whole power 3 by 2 ME MH the whole power 3 by 4 e power minus EG by 2 kBT. This is Ni. E is the charge of the charge carrier, mu E is the mobility of the electron and mu H is the mobility of holes. We are going to substitute Ni value here in this formula. Therefore, sigma I is equal to, in the place of Ni I am going to substitute 2 into 2 pi kBT by H square the whole power 3 by 2 ME MH the whole power 3 by 4 e power minus EG by 2 kBT. Up to this it denotes Ni. Then E, the charge of the charge carrier or the charge of the electron, then mu E plus mu H. Here, except this exponential form, the remaining can be considered as the constant one. That is, 2 is a number, pi is 3.14, kb the Boltzmann constant, H Planck's constant. Here T is the temperature of the semiconductor, Me the effective mass of the electron, Mh the effective mass of hole, and then charge of the electron, mobility of electrons and mobility of holes in the intrinsic semiconductor. But here the exponential value, the conductivity of the intrinsic semiconductor in this formula sigma I, it depends on exponential value of minus Eg by 2 kBT. Whereas here the another point is mu E mu H, the mobility of both the charge carriers. They have the temperature dependence value. So this T power 3 by 2 as well as this mu E plus mu H, these two are interdependent. Therefore, they can cancel each other with t power 3 by 2 term. Therefore, the above equation sigma I can be written as some constant value C1 and then e power minus Eg by 2 kBt, where C1 is 2 pi kBt by h square, the whole power 3 by 2, mh the whole power 3 by 4, e mu e plus mu h. This can be taken as a constant value. Then what for we are here? We need to find the expression for the band gap energy of the intrinsic semiconductor in terms of electrical conductivity. Now here I am going to take log on both the sides for this formula. Log sigma I is equal to log C1 plus log e power minus Eg by 2 kBt. So these are all to the base e. Here log sigma I is equal to, since log of a constant value can be taken as 0, and then we have log e to the base e as 1, we have minus Eg divided by 2 kBt, or minus Eg is equal to this 2 kBt is taken to the left hand side, we get 2 kBt log sigma I. That is the forbidden energy gap with the negative sign is in the left hand side, and then we have a temperature of the semiconductor, intrinsic semiconductor, and we have logarithmic value of sigma I. Now this can also be written as minus Eg is equal to 2 kb log sigma I divided by, in the numerator t is here, I am going to write it as 1 by t in the denominator. So this is the expression for forbidden energy gap or band gap energy of the intrinsic semiconductor in terms of electrical conductivity. If a graph is plotted with log sigma I along the y-axis and 1 by t along the x-axis, will get a straight line like this. That is, the electrical conductivity and the temperature 1 by t, it is decrease in temperature. That is, when the temperature is decreased, the electrical conductivity will also be decreased. That is shown in this straight line. When the temperature is decreased, then the electrical conductivity will also be decreased. If you take any 2 points are considered, if we take a slope, then this will give us dy and this will give us dx. So using the slope also we can find the forbidden energy gap of the intrinsic semiconductor. And we also have a negative sign here which shows that is, when the temperature is increased, the conductivity of the intrinsic semiconductor will also be increased. There will be movement of electrons and holes. The charge carriers will be moving, thereby we call it as electrical conductivity, then it will also be increased. This will lead to the decrease in the forbidden energy gap of the intrinsic semiconductor, that is given by the negative sign. Then secondly, we are going to express forbidden energy gap expression in terms of Ri, that is resistance of the intrinsic semiconductor. The same formula we are going to use, that is sigma I is equal to C1 e power minus Eg by 2 kBt. C1 e power minus Eg by 2 kBt. This is the formula we are going to use, the same formula. Now resistance, in terms of resistance we need to write. We know that resistivity is correlated with resistance, area of cross section of the material and the length of the material. I am going to write it with a subscript I, which shows that it is for intrinsic semiconductor. I denotes intrinsic semiconductor. Therefore, rho I is connected to sigma I with 1 by sigma I. That is resistivity, electrical resistivity and electrical conductivity are inversely proportional to each other. Therefore, this can be written as rho I is equal to 1 by sigma I. Therefore, here 1 by C1 1 by e power minus Eg by 2 kBt. It is resistivity is taken here, therefore inverse of conductivity is taken here. Then forget about this, therefore resistivity can be written as Ri A divided by L is equal to 1 by C1, and this e power minus x in the denominator is taken to the numerator as e power x. Therefore e power plus Eg by 2 kBt. Then Ri is kept in the left hand side itself, and the remaining parameters are taken to the right hand side accordingly. Then we get L divided by AC1 into e power Eg by 2 kBt. Now L is the length of the intrinsic semiconductor, A is area of cross section of the semiconductor, C1 is already a constant. Therefore, together we are going to write it as C2, which is another constant. Therefore, Ri is equal to C2 e power Eg divided by 2 kBt. So, this formula is similar to this formula. Sigma I is equal to C1 e power minus Eg by 2 kBt. Here C2 e power Eg by 2 kBt. Similarly, taking logarithm on both the sides, we get log Ri to the base e is equal to log C2 plus log Eg divided by 2 kBt. In the same way, we are going to cancel this and this becomes 1. Therefore, log Ri is equal to Eg divided by 2 kBt. So, this is similar to this particular formula. Therefore, Eg, the forbidden energy gap of the intrinsic semiconductor, is equal to, taking this towards the other side, 2 kBt log Ri. Or Eg is equal to 2 kB log Ri divided by 1 by T. That is, this is taken to the denominator of the denominator. So, here we have negative sign which shows the forbidden energy gap is decreasing or reduced with increase in temperature and increase in conductivity, whereas here it is a positive value which denotes if there is increase in temperature of the intrinsic semiconductor, the conductivity increases, but the resistance or resistivity will be decreasing. Therefore, here if conductivity is increasing, the negative sign will be there in the formula. It shows that the forbidden energy gap will be decreasing, whereas this shows that the resistance or the resistivity is decreasing. Therefore, the forbidden energy gap will be increasing. If a graph is plotted with log Ri along the y-axis and 1 by T decrease in temperature along the x-axis, that is, it will be when the temperature is decreasing, there will be increase in the resistance of the intrinsic semiconductor, that is, it is decrease in temperature. There the graph shows with decrease in temperature, the conductivity also decreasing, whereas here with the decrease in temperature, the resistance of the intrinsic semiconductor is increasing. Thereby, the forbidden energy gap value will also be increasing if slope is taken with any 2 points dy dx. Therefore, the forbidden energy gap formula can be taken as 2 kb log Ri divided by 1 by T, and in terms of conductivity minus Eg is equal to 2 kb log sigma I divided by 1 by T. So using this slope for both the cases, we can calculate the forbidden energy gap or the band gap energy of any intrinsic semiconductor like germanium or silicon.